All right. Just add a new page here, maybe. There we go. So 35. Oh. Oops. 35 has got 2 to the x equal to 3 to the x plus 1, right? Yep. So what is it about this one that's given us a little bit of an issue? What stumps you on this one a little bit? Say again? So our bases are different, so we can't just use 1-to-1, right?
There's an exponent on both sides.
And we've got exponents on both sides. So what probably should be our method for solving this? Take the log of one side?
Well, like, you can log both sides.
Logging both sides, right? The trick is, which base should I use? Because on one side, the base of my exponential is 2, but on the other side, the base of my exponential is 3. So which base am I supposed to use? In all honesty, it wouldn't matter. Okay? And quite frankly, if you look at this and go, wow, I have these different bases, maybe you don't even want to go with either one. Maybe you want to just go with one of the more familiar ones like common log or natural log. Okay? So let's say we just totally flake out here and go natural log on both sides. Okay, so why does that help? Even though I didn't match up bases, why does that still help me?
You can multiply the exponents in the front.
Yeah, so now I can go to the property that says when I have natural log of something being taken to an exponent, I can rewrite it as the exponent down in front being multiplied by that log. So I can bring my x down in front here, and I can bring my, whoops, sorry, again, x ln 2, and then I can bring this whole x plus 1 to multiply down in front here.
Is that always?
Okay, now make sure that you're keeping that x plus 1 as a quantity. Okay, don't bring it down and then trick yourself into thinking that you're only multiplying the 1 times the ln 3, right? ln 3 is going to have to get distributed here. And so basically that's how we go through this now. In order to get to the x by itself, we need to get rid of the parentheses on this side by distributing. So this is going to become like an x times ln 3 plus an ln 3. This is an x times ln 2. And so what do I need to do to get x by itself? I need to get all the x's on the same side. So I'm just going to subtract my, stop that. My brain gets all mushed up and my ln's become h's. I'm just going to subtract my x times ln 3 over here to get it all on the same side. And then having both of these terms with a common x in it means I can factor x out. So ln 2 minus ln 3 is going to equal my ln 3. And so ultimately, to get x all by itself, this ln3 is going to get divided by whatever ln2 minus ln3 is, and now you pull out the calculator and punch the buttons. Okay? So it's not pretty necessarily, but it's just a matter of using the properties that we know to be able to get those x's out of the tower, out of the exponential spot, get them down there where we can work with them, and then remembering that when we take any kind of log of a number, it is just a number. And so we're going to work with it just like we would if it was, x times 5 and x plus 1 times 7. Right? The 5 is going to be the coefficient over here, the 7 would get distributed. We're going to do those same kinds of steps that we would do with any nice looking number with these log of numbers until you ultimately get down to x being by itself, and then you take out the calculator and punch the buttons. Okay? Does that make sense? So 37 would be the same kind of thing. We would have to take the log of both sides with just some arbitrary log, whatever we want to pick. I'll come back to 41, Casey. I'm not forgetting about you, but since this one's similar, we're going to go ahead and look at this quick. So 4 to the x equals 5 to the x squared. So let's give common log a chance. Don't want to be discriminatory here.
So why are we doing log this time instead of natural? Oh,
Because I felt like it.
Oh, okay.
Because I didn't want log to feel lonely. It doesn't matter.
Oh, it doesn't matter.
That's my whole point. It does not matter. As long as you take the log of something so that we can use our property to bring the x's down, it doesn't actually matter what log you use. Now we talked about in class about when you can be strategic about the type of log you choose because things can cancel. Right? But in this case, because I have two different exponents that have two different bases, I'm not going to be able to pick one strategic log that cancels everything out. So I can just pick whatever. So if you wanted to make this natural log, okay.
Okay.
I just decided to choose, common log because I didn't want it to feel left out.
Okay.
Because logs have feelings. So. All right? And just to make a point that it doesn't matter what you choose. Usually, if you can't pick a strategic log, go with one of the ones that you're familiar with, the LNs or the LOGs. Okay? All right, so same idea. We're going to bring x down in front of this one. And we're going to bring x squared down in front of this one. Okay? And then same thing. In order to get x isolated, I have to first get them on the same side of the equation. Now I'm going to choose to subtract this one over here this time because I want to keep my x squared positive. Okay? So we're going to say 0 equals x squared times the log of 5. And we're going to subtract from that x times the log of 4. Mm-hmm.
Since that's being multiplied, can't you just divide x by x squared and remove the log 4 over the other side and the log 5 divided by log 4?
No. Why not? Why do we not just want to divide both sides by x? Because any time you divide by a variable, you risk losing a solution. Okay? Anytime you divide by something that has a variable in it, and it actually cancels it out, it actually makes it disappear, what you've made disappear along with it, quite possibly, is one of the solutions. Okay? So in this case, we do not want to just multiply both sides by x and say, oh look, I just have an x left. Woo, yay! you're going to find that that is one of the solutions. The answer you would get from doing that is one of the solutions, but it may not be all of them. Okay? So now that I have them on the same side, can I factor something out? X, right? So I can factor out an x, and that leaves me then with an x log 5 minus a log 4. Now what do I do with that?
Well, you have one solution, 0.
Why?
Because if x was 0, then it will have to equal 0.
Okay, so because we now have factors, the obvious one is that, okay, well if x was 0, then the whole thing would equal 0 and everything would work, right? So my first factor of x could equal 0, which is, boom, one of my solutions. But then I do the same thing with the other factor. Because by setting this all equal to 0, even though it's not a nice, pretty factored quadratic, it is still two factors being multiplied, and the zero product property still works. So now I have to take this x log 5 minus log 4 and set it equal to 0 as well, because maybe it was that factor that was 0 that gave me the 0 answer. So now can you solve for x? Whoops, I lost a 5 here. Right? And then you punch it in and find out what that is. So if we had done what Rohit suggested and did that division of x up here, this would have been the only answer we got. But this is also a possibility, and we would have lost it when we divided the x out. So both of these should be solutions. Okay? So all that stuff you've learned before, no, you don't get to flush it. You have to keep on, hang on to it. Because in pre-calc, a lot of pre-calc, which is why I like pre-calc so much. Pre-calc, I think, is the class where you finally get to start answering that question of why are we learning all of this math? I know that's not always the word you put in there, but you know, you've gone through Alg 1 and Geo and Alg 2, and you know that question is like, why are we learning this? Why are we learning this? Why are we learning this? Well, in pre-calc, you start seeing why you were learning this. You start seeing that you now have enough math in your math toolbox that you can start doing the kinds of problems that need those tools. And you have enough of those tools now to put together the IKEA chair. Right? Like you have enough tools now that you can put together some pretty complex problems. But we have to remember that the tools are in the toolbox. Have you ever seen a toolbox that has like the tray on the top and then deeper underneath? Well, we can't just open up and think, oh, well, there's the tray. Here's what I've learned in the last week, and that's all I've got. We got to lift up the tray and remember there's stuff down there in the bottom we can use too. So we have to remember that we have all of these other techniques at our disposal. Zero product property is not just for quadratics. It's for any time where we can set up two factors and make them equal to 0. Boom, that means I can set each factor equal to 0 and solve things out. Okay? All right, so back to 41, because there's a question about that one. Let me add another page here. 41 said 500 over 100 minus e to the x minus 2 power equals 20. So what do you suppose we need to do first?
Multiply both sides by 100 and this side. E to the x.
Yeah, because ultimately, again, our first step in these equations is we need to get the exponential part isolated if we can. Because then we'll know what to do in terms of logarithms or solving or using one-to-one or whatever the case is. So I need to do some algebra first here to try to get that e to the x minus 2 bit all by itself. So the first thing is to get it out of the denominator by multiplying both sides by that denominator. Okay, that allows us to cancel it here, but I didn't make it disappear, right? We're canceling on one side, but it's still over there on the other side, so that's all leave. So now I've got 500 being equal to, by what?
You can divide by 20 both sides by 20.
Okay, so if we keep it in the factored form like this, whoops, minus e to the x minus 2, because of the numbers we have here, we can actually divide by 20. Or the other option would be distribute the 20 and then work from there. So if I divide both sides by 20, 500 becomes what? 25. Okay, now what?
I moved the 100 over.
Move the 100 over, so that's going to be a negative 75 equal to negative e to the x over 2. And then,
I did change it to a natural log.
before you do that, get rid of the negatives. Now does that look doable? Yeah. Can I pick a strategic log this time?
Natural log.
Yeah, natural log, because I just have that 1 there, so I can pick the matching base, which is going to be natural log. So I do that to both sides, which means this cancels, and I just have the x over 2 left. Equals. And then last but not least, to get x by itself, multiply by 2. So what I'm going to punch in the calculator is 2 times the natural log of 75. That should give me the decimal answer. Okay, so 41 is a lot more about the algebra you need to do up front to get your exponential piece by itself. Once you get the exponential by itself, it becomes pretty simple. Okay, everybody okay with the rest of the exponential equations? All right, now take a look at the logarithmic section. I would hope that a lot of those would make some sense to you and you could figure them out. So what I really want to focus on is which ones were the ones that stumped you. Which ones did you look at and go, oh, geez, no idea. So we're talking 45 to 61 now. Casey, go for it.
It was like 55, 57, 59, and 61.
Okay, so the bottom half, basically. All right, 57 is a good one. And, okay, 59 should not have stumped you. Because what can you do with 59? If you've got the log of 3x plus 4 equals the log of x minus 10, what can you do with that?
You can set you can just start with the long part. I think I just like forgot what I was doing and stopped.
So 59 should not be a troublesome one, right? That's just one-to-one property. Now, let me think about this for a second. What happens when you set 3x plus 4 equal to x minus 10? What do you get for x?
Negative 7.
-7. Is that my solution? Can I write x equals -7, put my little box around it, and go on? No. Because with logarithms, we do have a restricted domain. So we do have limits as to what x's we can use. Okay? And so when you're doing logarithmic equations, once you've done the algebra to get down to what x appears it should be, you always need to go back and check it in your original equation to make sure that it doesn't make anything end up with the log of something less than or equal to 0. So when I end up with an x of -7, if I actually put that back in to that equation in number 59, I end up with a log of -21 plus 14 would be a -17. And on the other side, I end up with a log of -17 as well. But I can't take log of something negative. So even though I get a value of x equals -7, my answer to number 59 is no solution. Because putting that -7 back into the equation gives me something that can't happen. So that -7 is what we call an extraneous solution, and we cannot use it. Okay, so the solving, the algebra part should be easy. We're just taking the 3x plus 4 equal to the x minus 10. The tricky part on 59 is knowing that when you get that -7, it doesn't work. And so your answer is actually no solution. Okay? All right, back up to 57. So 57 gives us natural log of x plus 5 equal to the natural log of x minus 1 minus the natural log of x plus 1. So natural log is similar to exponential in that we basically have two ways of going about it. One is to try to set up a one-to-one property, like 59. I got a log of something equal to a log of something. That means the somethings have to be equal to each other. I set that up as an equation, I go with it. Okay? But when that doesn't work, when I don't have logs on both sides, I can't just get it to be a log of something equal to a log of something, then your other option is to use your properties and do a rewrite. So change your logarithmic equation back into an exponential equation and see if you can work it out that way. Okay? So in this case, obviously looking at it initially, it's not a one-to-one. But remember, it's not about whether it is, it's about whether it could be. So is there any way that I could make this a one-to-one? How?
The right side could be the natural log of x minus 1 over x.
Right. So here's where our properties kick in. So anytime you actually have logs on both sides, really try to set up a one-to-one if you can. Usually the rewriting kinds of problems are if I only have a log on one side or the other, but not both. But if I have logs on both sides, there's a really good chance that I can do something to get it to be log of something equals log of something, and then I can put the two somethings equal to each other. So in this case, subtracting these two logs fits right into our difference property that says, well, I can rewrite that as this. Now I've got one-to-one. So now what I'm really going to solve is x plus 5 equals
x minus 1 over x plus 1. Okay, so what's my first step for that?
Get the x plus 1 out of the denominator.
Here they cancel. Here I'm going to multiply that out. So what do we get? X squared. That's a good start. Plus 6x plus 5. And that's still equal to an x minus 1. And so now if I pull those over, I end up with x squared minus 5x
It's actually
plus
It's
6.
plus 5x. Because it's just 6x minus x.
Oh, sorry. I see what you, okay. Plus 6 equals 0.
But it-
I can do that, can't I?
X 3, x 2.
Which means, according to this, x's could be. Now the question is that what x's are?
It can't be in neither. Yeah.
Can't be either one. Works great here. That's all hunky dory. But once I put it in here, things kind of blow up. Okay? And it's true for both of them. With both of them being negative, if I put it into that natural log, things aren't going to work. So, another no solution. Okay, so exponentials are nice because with an unrestricted domain, pretty much if you do the algebra right, whatever you get, you get. It works, it's fine, it's all cool, no worries. But with logarithms, because we do have that restricted domain, we always have to check our x values. And it's not necessarily about x being negative, it's about what it makes happen in the original equation. If the x I get ends up making anything in my equation, an expression where I take the natural log of something negative or a natural log of 0, then I can't use that value for a solution. Okay? 61 is a similar kind of problem and yet quite a bit different. In 61, we start off with the log base 4 of x minus the log base 4 of x minus 1, and that is just equal to a 1/2. So do you think we'll be able to set up a 1-to-1 on this one? No, because I only have logs on one side of the equation. I don't have it on the other side. But even to be able to do the rewrite, I need my equation to be a single log on one side equal to whatever it's going to be equal to on the other side. So I still need to use my property as a way of condensing these two logs into one before I can actually do the rewrite. So what would this be as a single log base 4? Okay. Now I have the log base something of something equals something. Now I can do the rewrite into exponential form. So what would this look like as a rewrite?
Probably 4 to the power of half is equal to x over x.
Does that help? Yeah, because what is 4 to the power of 1/2?
2.
2, right? Square root of 4. So now I'm just solving that. So same thing, we're going to multiply both sides by that denominator of x minus 1. Cancels here. I end up with 2x minus 2 here. now equal to x. So if I subtract the x over here and add that 2 over there, and will that one work? Yes. Putting 2 in here is fine. Putting 2 in here, 2 minus 1 is positive 1, that's fine. So this really is my solution this time. Okay. So both exponentials and logarithms basically come down to, can I set up a one-to-one? If not, then I'm going to work on it either by doing a rewrite, or with exponentials, kind of the equivalent of the rewrite is logging both sides, and then work it out from there. If you can pick a strategic log that's going to wipe out a base for you, go with that. If it's an equation where that doesn't really quite work, then just pick something familiar, either a common log or a natural log, and do that to both sides. Okay? Any other questions? All right, how about the word problems? How did those go? You had number 71 and number 83. Did those make sense? Yeah, are you okay with those? Okay, good. All right, so what we're going to do today then is actually give you a bit more practice with using these logarithmic and exponential kinds of equations, working with them both in terms of graphing and in terms of solving. And we're going to do that with some real life problems. And so what I've done is I've taken 6 problems and I've set them up in folders. And they each represent a different type of model that is common with exponentials and logarithms. So we've got exponential growth, a couple of different examples of that actually. We've got an exponential decay model, and then we've got 3 interesting logarithmic models. One is just a logarithmic model with earthquakes. You've probably heard before that the Richter scale is something based on a logarithmic model, so we've got a problem like that. And then we've got something called a logistic growth model. I guess these aren't actually logarithmic, I apologize. This is the only logarithmic model. These 2 are variations on the exponential model. So a logistic growth model is something that starts out looking very exponential. It has that rapid growth really quickly, but then there's something about the situation that eventually slows down the growth. Okay? And so you get graphs that look a little bit like this, where at the beginning you get that really quick amount of growth, but then there's something that starts slowing things down and things kind of plateau. So we've got one example of that kind of a problem. And then we've got something called a Gaussian model, which any of you who have ever taken statistics might refer to as a bell-shaped curve. Okay? Bell-shaped curves are actually a type of exponential model. And so we've got an example of that. So what I'm going to do is I'm going to hand out one folder to each group of tables. Inside of the folder is the actual problem. And there are 4 copies of the problem so that you can each look at your own copy. But I'm asking you not to write on the papers in the folder. Do your writing in your own notebook. Okay? Because when you're done with this problem, you're going to put all of them back in the folder and you're going to pass it on to the next group. So they need to be getting a clean paper without your scratchings on it. Okay? So do all of your work and all of your writing on your own notebook, but this should allow you to each be able to look at the problem in front of you and not be trying to, what did it say over there? Okay? Timing-wise, we may not get through all of them. but I think it'll be a good practice to get through as many as we can. So I will pass them out. You'll start with the one that I give you. We're gonna go 5 to 10 minutes on each one, kind of judging by when people are finishing up. Maximum of 10 minutes on each one. And then you'll put your papers back in your folder and we'll pass it to the next group and you'll get a new problem to work on. You can work on it together, you can discuss it at your table, think it through, but basically what you're doing is you're getting out the toolbox. You are now using the tools you have at your disposal, both in terms of working with exponentials and logarithmics and in terms of other arithmetic that you know how to do, and algebra that you know how to do. Okay? And you're putting all of that together now to try to build yourself an answer to a problem. Okay? So this is your IKEA chair for today. You're using your tools to put together your IKEA chair. Okay? Make sense? In the last 3 to 5 minutes, we'll kind of wrap things up. I'll tell you a little bit about where you can find answers to these when you're finished. And your homework for tonight then, there's a few more problems similar to this that you'll be doing for homework. And then anything from that logarithmic section that you didn't get through, it would be good for you to go back and just redo them yourself. Maybe you saw it up here now, but just go back and do it for yourself to make sure that you've got all the steps down. Okay? Make sense? Any questions? All right, so you will need your calculator, you will need your notebook, you will need your teammates, because you're going to want to talk these out and think about possibilities. You don't really need your computers. Well, I take that back. Keep your computers there. There's one problem where I'm going to ask you to look something up. So keep your computers there for that problem, but most of the time your computer should be shut. Okay, you don't need them for most of the problems. Okay, you need to be engaged in part of what your group is discussing. All right, here we go.